things that you learn in Math 1. The first product that you're going to have to know is the product property, which means if I have a base raised to the m power times a base raised to the n power, that is going to give me the base to the m plus n power, which I think is easier to think about whenever you just have numbers in there, right? So the example here, if I have x to the 5th times x to the 3rd, then I just add those exponents together, which most of the time we don't even write this middle step right here, and we would get x to the 8th power, right? So this is something that we learned in Math 1. When I teach it in Math 1, my kids do so good at this until I teach them the power property. And the power property is raising a power up to another power. And so if I have a power raised to another power, I have to multiply those powers together, right? So, for example, if I have x to the 5th to the 3rd power, that is x to the 5 times 3, which is 15. And once I teach them that second property, they start getting it mixed up with the first property and can't remember which one to do. What I do a lot of times in math in general, if I have trouble keeping things straight, I try to really make sure I know the most basic example. So if I think of something like these examples here, but like x squared times x to the 3rd, I know that's x to the 5th, right? Whereas x squared to the 3rd power, right, will be x to the 6th. And if I have that straight in my head, when I get things that are more complicated, I can kind of write that down and think to myself, well, how does that apply here, all right? So these two we definitely need to know and have straight in our minds, right? Now, negative exponent property. I did not teach any of you except for Granger in Math 1. But when I teach, and I don't probably no other teacher has this innovative way of teaching that I teach whenever I teach negative exponents. What I tell students when they're dealing with negative exponents is that negative exponents are like bad children. And how do you fix bad children? You throw them in the basement. See, Granger remembers what to do with bad children. So whenever you have negative exponents, they are like bad children. So if you lock them in the basement, it makes them better, and notice their negativity turn to positivity right there, and they're all cured. This also happens sometimes. You may be thinking, Miss Hyatt, I don't have a basement at my house to lock the bad children in. Sometimes you might be in this scenario where you've got 1 over x to the negative 2. Most houses, if they don't have a basement, are going to have an attic. So if you have negative exponents that are in your denominator, you can lock them in the attic and just get x squared there on top. Basically, you're moving it to the other side of the fraction bar to get rid of it, right? So if I have something like x to the negative 3, I got 1 over x to the 3rd, right? And then negative 2 to the negative x, I can move that to the bottom, and I'll get 1 over x squared. All right. This is particularly helpful because you're going to be asked to do some things like, just to give you an example, 5 to the negative 3rd power without a calculator, right? And so you probably might know how to type that into a calculator, but you don't know how to do it otherwise very well. So if you have to figure out 5 to the negative 3rd without a calculator, what you can do is just send that to the basement. It's really 1 over 5 to the 3rd. And then figure out what 5 to the 3rd is. So 5 times 5 times 5 is going to be 125. So 5 to the negative 3rd power is 1 over 125. That messes students up too sometimes if that's not a negative number, right? You get a very small positive number whenever you do that. Okay. Questions there? Okay, so the same rules are going to apply whenever we're working with horizontal transformations. So, for example, here, I have f of x equals 4 to the x plus 2 power, right? So, one way I can think about this is that that is y. Right. What has happened? Why is it not letting me write? I don't understand. It was working just fine. There we go. All right. So, this is the graph of just y equals 4 to the x power shifted. Which way does it go? Left 2. Right? So that is one possible description of what this graph would look like, right? It would just be 4 to the x power shifted to the left 2. However, if we use properties of exponents on this, if we use properties of exponents, we also, oh wait, I think I'm getting ahead of myself. I think he's doing this in a minute. Hold up. We're not going to do that. We're just going to tell what transformations we have here. All right, so that is inside of the parentheses. That would be shifted left 2. That's all we've got to do for this one. What about B? Almost. It is a horizontal stretch or shrink, but everything on the inside of the parentheses, which when you're in that exponent for an exponential, there aren't parentheses there most of the time, but that's where your parentheses would be. Everything's backwards. So if we put a big number, like 3, it actually makes it smaller for that. So this would be y equals just 2 to the x power would be compressed, or it may just say dilated, horizontally by a factor of 1/3. All right, what about C? Uh-huh. Dilated can be bigger or smaller, so it would be perfectly correct for him to say dilated. If we want to be more specific, is it going to be a compression or an expansion? It's expansion. What I like to do with this sometimes is I like to write it this way. Instead of writing it as x over 2, I like to write it as 1/2 times x. That is equivalent because x divided by 2, there's a 1 right there, right? So if I write it, if I sort of separate my coefficients and my x, that's still equivalent because the x right there is understood to be over 1, and if I multiply them back together, I get x on top, I get 2 on the bottom, right? While we don't really talk about that number dividing very much, most of the time if you have division, you can make it a fraction for that. And so in this case, this would be y equals 9 to the x power. And we could use the word dilation, and sometimes they will use the word dilation. Sometimes they might be more specific, and this is going to be an expansion or expanded horizontally by a factor of, what's my factor for that one? 2. It flips the fraction. Everything is upside down there. And it would be perfectly okay to write that same thing and use the word dilated instead of expanded, because your factor should tell you whether it's getting bigger or smaller. If your factor is bigger than 1, it's expanding. If it's smaller than 1, it's compressing. All right. And how about this last one? Who can tell me what's happening there?
Let's go to the right one.
Correct. Right one. So it would be y equals 5 to the x shifted right 1. Now, I want to do this real quick just to let you see kind of what's happening here graphically. So we're going to go to Desmos, even though they won't let us use Desmos. It's still helpful to see what's happening a lot of times. Let me graph y equals 4 to the x power, and I'm going to graph y equals 4 to the x plus 2. And I'm going to tell you the truth. When I'm looking at graphs, I think it's hard to tell what's happening here, right? Definitely I can see the shift, but it's kind of hard on exponentials for me to see what's happening. Let's look at the next one. Y equals 2 to the 3x, and then let me just graph y equals 2 to the x. There I can kind of see. It kind of helps that it's not a shift here, because you do see they have that same point right there. But as far as like seeing a factor, it's really hard to tell. That's one of the reasons we need to know from the equation, right? Now, let me actually go back. Let me put that y equals 4 to the x and y equals 4 to the x plus 2. I'm going to put that up here. Now, here's something this is the main thing that we're learning from this section. Let's think about this product property in reverse. So I'm going to write this out even though he's got it there. If I have 4 to the x plus 2, that is equivalent to 4 to the x times 4 to the second, right? Because that product property tells me that if I'm multiplying two things with the same base, I would add their exponent together, right? Well, I could rewrite this. I could put that 4 squared first, and then my 4 to the x, and then I would get 16 times 4 to the x power. Now, if I'm looking at 16 times 4 to the x power, is that a horizontal shift? It is not, right? Horizontal shifts happen up here in the exponent, right? So this right here is a vertical dilation by a factor of 16. So if we flip back over here to Desmos, and if I graph 16 times 4 to the x power, it's exactly the same as the red graph that I have there. So while when I'm looking at A, it is most easily shown as a horizontal shift, it also has a vertical stretch that is equivalent to it. Sometimes it's really hard for me to picture that. Let me do this. Let me make this an A right here and add a slider. So now my blue graph is right here, and as I make that number bigger, you can see this is the original. This red is what I would have here. So that graph is getting stretched vertically is what's happening. And as I make that number bigger, it's stretching it vertically. It really looks like it's sliding it left instead of stretching it vertically, because there are equivalent expressions for that. So it won't let me go to 16 here, but if it did, when I finally get all the way to 16, they match. So whenever we're dealing with exponentials, we can have horizontal translations that are equal to vertical dilations here. So one of the things that we're going to do here, it says for each of the following exponential functions, write the horizontal translation, and for each write an equivalent representation that has a vertical dilation and no horizontal translation for this. Sorry. For this, we've got 2 to the x plus 3. So for this, let's start first of all just telling what we have here. So f, actually I should say, hold on, let me not call it f. F is what we've got right there. Let's just say it would be y to the 2x. A y equals 2 to the x shifted, which direction? Left 3, right? That would be the horizontal shift. But it asks us also to do a vertical dilation that is equal to that. It asks us to put it in the a times b to the x form. So if I do that, I can write f of x as 2 to the x times 2 to the third power, right? And then probably I won't put that 2 to the third power first. I could have done that to begin with. And what is 2 to the third power? 8. So I've got 8 times 2 to the x power. And there's my a times b to the x formula, which a lot of times is what we would rather see, because that gives us like an initial value and a growth or decay factor that we're dealing with. So while it could be y equals 2 to the x shifted left 3, it also could be y equals 2 to the x expanded vertically by a factor of 8. Right, those are both correct in this case. All right, B is a little bit different because we have a minus. Now we're going to still talk about this. This would be y equals 3 to the x power shifted which direction? Right 2. So that is a possible description here. But I also here could make this 3 to the x power times 3 to the negative 2 power. Which normally we'd write that 3 to the negative 2 first. Ooh, what is 3 to the negative 2? Good. That's going to be 1 over 3 squared times 3 to the x power, which is going to be 1/9 times 3 to the x power. So this would be y equals 3 to the x, not shifted right 2, but what? We multiply. So this would not be shifted right. What would this one be? Compressed vertically. By what factor? 1/9. Right, we don't have to flip it whenever that number's on the outside of the parentheses there. Which there are no parentheses there, but they would be just in the exponent. Okay. C is going to be even a little bit different because this time we do have a number out front, right? If we are looking at this originally, right, we would actually have two transformations that had happened to our y to the 3x. That 4 and that plus 2. Okay? So what does the 4 do to this graph? Expanded vertically by a factor of 4. And what does the plus 2 do? Sorry. I do need to talk to Walgreens. Left 2. Okay, so our original already had two transformations. But that 3 to the x plus 2, we could write this way. So we can split it up. We've got 4, 3 to the x times 3 to the second. Which, if I put that in a different order, I could do 4 times 3 squared times 3 to the x. 3 squared is 9. 4 times 9 would give us 36 times 3 to the x power. Can I multiply that 36 and that 3 together? I cannot, because 3 is being raised to a power, 36 is not, so I can't put those together. So if I write it this way, there's only one transformation, right? This would be y equals 3 to the x expanded vertically by a factor of 36. Okay, questions there? All right, now, we also can use the power property of exponents to show that every horizontal dilation is equivalent to changing the base of the exponential function. Okay? So, whenever we have f of x equals b to the cx, we can write that as b to the c to the x. So, for this example that's given here, we've got y equals 9 to the 2x, right? So, it can be written like it is here, and it would be, like as it is, it's y equals 9 to the x power that is compressed horizontally by a factor of 1/2. But this also can be written this way, 9 to the second to the x power, right? It also could be written this way, 9 to the x squared. It really doesn't matter which one's on the inside and outside. But if I'm changing the base here, this one's the one that's useful because I can't do 9 to the x, so it would just be a more complicated function. But here I can do 9 squared. What is 9 squared? 81. So this is 81 to the x power. So D would be equivalent to 9 to the 2x. All right, 4 is harder because 4 was not set up that same way, right? 4, we don't have like 4 to a 3x or something where we can break it down. To me, this one is more difficult. This time, we need, it looks like all the bases turn to 16, right? So, if we kind of think about what we have, if all the bases turn to 16, I'm kind of thinking it's not going to change that first number, but maybe. But that exponent only goes with the 4. So, I'm kind of thinking A and B should be out because this exponent, unless there's an extra set of parentheses, it only goes with the 4. So, whatever you manipulate here is not going to change that first number. So, I'm thinking A and B are probably bad choices, which means over here, I've got 9 times 16 to the x divided by 2. I don't want to deal with that one. Let's go down here. Let's do this one. This one is 9 times 16 to the 2x. That'd be 9 times 16 squared to the x power. And 16 squared, I'm not even sure if I know. 256 maybe? 16 times 16. Anybody got the calculator? Grab mine. I think it's 256. 16 times 16. Yeah, 256. So that'd be 9 times 256 to the x power. Is that equivalent to what we started with here? No. So that one is not it. I'm thinking C is probably going to be the right answer. So I've got 9 times 16 to the x divided by 2. Now, we don't have any special rules with division, right? But we can write this so it's not division anymore, right? 9 times 16 to the 1/2 x, which will be 9 times 16 to the 1/2 to the x here. Oh, do you guys know how to do 16 to the 1/2 without a calculator? I'm thinking. It is not, because it's not 16 times 1/2. It's 16 to the 1/2 power. So I think this is maybe a gap we're going to have. We may need to do a little practice with this. I don't know that you do fractional exponents anywhere anymore. It used to be in Math 1, I think, but I'm pretty sure it's not there anymore. If I have A, no, don't use A, right there. If I have, let's call it B to the A, actually, sorry, I don't like these letters. Let's use A. Let's do X to the A over B power. Right, so I've got a fractional exponent, which is what I've got here. This is going to be equivalent to the B root of X to the A power. So I think this is something we should have already learned that is not in North Carolina curriculum. So it's being introduced here like you already know what to do with it, but we don't. So let's think about that 16 to the 1/2 power, because you're going to see this not on tomorrow's quiz, because this stuff will not be on tomorrow's quiz anyway. But you'll see this without a calculator. You won't be allowed to use a calculator on this part. So I always say that roots go on the bottom of a tree. So the bottom of the fraction is the root out here. So this would be a root. The bottom goes out here, which is a 2. We got 16 to the first power on the inside. Is that 2 really necessary here? That's just a square root. If it was something else, it would be necessary, right? If it's a 3 or a 4 or a 5, you have to put it there. But that is going to be the square root of just 16 to the first power of 16. What is the square root of 16? It is 4. So this is 9 times 4 to the x power. And that does match what we're supposed to start with. So C is our answer.
What would you do if there was a different number in there? How would you solve that?
If you have something like, for example, like the cube root of 8. Think about like square root of 16 first. When you have square root of 16, it's saying what number times itself equals 16. Yep. So over here, like let's say we had cube root of 8, it'd be what number? Yeah, times itself 3 times. Equals 8. And then so cube root of 8 would be 2. And they won't ask you to do that without a calculator unless it's a whole number answer for that. So you're probably going to see things like 8, maybe 125 is 5 times 5 times 5. 64 would be, yeah, it's not going to be huge for that. Okay, so you got about